Alrighty, thanks everyone for your patience. So we have a talk from Brandon Jones at Google. He's going to talk about the WebGPU Vulkan backend for Android. Please, Jen, take it away.
Thank you. As he said, my name is Brandon Jones. I'm an engineer on the Google Chrome team, and I've spent the last decade or so working on various graphics bits within the browser. That includes implementation of WebGL. I co-created the WebXR API, and lately I've been working as spec editor on the WebGPU API, which is the topic of today's talk. This is going to be a little bit of a high-level post-mortem of sorts on our implementation using Vulkan as one of our backends. But before we get into the Vulkan bits, I want to talk just a little bit about what WebGPU actually is, if anybody in the audience isn't familiar with it. WebGPU is a modern graphics and compute API for the web. It's something of a WebGL successor, although it's being developed under the W3C rather than Khronos. And it's an abstraction over Vulkan, D3D12, and Metal concepts, adhering to a lot of the patterns of that API while trying to avoid some of the minutiae of like memory management and barriers and whatnot. We focus on the common feature set of all those APIs, but we do have an extension mechanism to allow us to extend the API in the future and expose features that are common but not ubiquitous, like texture compression. Now, the API is designed with the web in mind. The spec is stated in terms of JavaScript, but we want it to be useful in native context as well. And so, excuse me, there are native headers that we have on the Google side. We have built a C++ implementation that we call DOM. That's what powers the Chrome implementation of WebGPU. Mozilla has been building a Rust implementation that they call WGPU. And we actually see that that's getting a lot of pickup on the Rust side. It's one of the more popular graphics crates in that ecosystem, which is really, really encouraging. And there are a lot of community bindings coming up for other languages. So if you want a WebGPU in Python, you can WebGPU in Python. We are shipping today. We've actually been shipping on Windows, Mac, and Chrome OS since last April. And we're shipping on Android devices as of like 2 weeks ago. It's a very recent thing. Now, initially, we're only shipping on Android 12 and greater if you have an ARM or a Qualcomm GPU, but we do intend to expand that in the future. Those are just the devices that we were able to get the best access to and the most testing done on. We also see a lot of progress in the Firefox and Safari backends. They're both behind flags right now. Neither are feature complete, but they're making really, really good progress. I am not going to give shipping estimates for teams that are not my own, but I would fully expect that we're going to see WebGPU be a standard part of the web platform across all major browsers pretty soon. Now, because this is a graphics API, I'm going to show some pretty pixels. Also, because this is a remote presentation, it's going to come across at like 2 frames per second, but I promise you it looks better. Now, the fun part is because this is a web API, chances are you can go to that URL or the QR code and view this on a device that you have in your pocket or your backpack right now. If you have an iPhone, I'm sorry, I hear the EU is working on that. So here we go. This is a demo from a company called Play Canvas. They've had a really good, 4 frames per second. They've had a really good WebGL-based engine for a good long time. It's got a very nice web-facing editor. It's a little bit like Unity for the web. And they've recently been doing a WebGPU port. This is one of the initial demos that they put out, showing off their area lighting. Excuse me. This demo also happened to surface several bugs in our implementation, so I've spent an awful lot of time looking at that car. Now, this is usually the part in the presentation when I'm talking to a bunch of web developers where I would espouse the benefits of these newfangled compute shader things. I don't think that's going to play quite as well to this crowd, so instead I'm going to talk about the web-facing benefits of no build step and deploying on Android without ever touching a Gradle file. Yes, see, you get it. Thank you. So spending like 60 seconds just to look at some of the code to give you a feel for what this actually looks like in practice. We're not going to go through it line by line, but this is all of the code for getting a single like hello triangle type application up on screen. It's under 100 lines. If I tell a room of web developers that, they think they recoil in horror that we could have designed something so complicated. And if I tell a room of Vulkan developers that, they think we're cheating. But if you look at this, you can see that there's a lot of parallels to Vulkan. It looks a lot like Vulkan as you squint. We have adapters, which are kind of the analog for VK physical devices. We have devices, which are the analog for VK devices. We have canvas contexts, which are kind of like surfaces and swap chains all smushed together. And the list goes on, shader modules and render pipelines and buffers and command buffers and render passes and all that sort of thing. It should be supremely unsurprising what you see here. The critical part is what you don't see here, which is things like allocators and pools and caches and barriers. And that's because when developing this API, we were able to use the hindsight of both watching the native APIs ship and how they were adopted by various people in the industry, and from the decade plus of shipping WebGL and seeing how developers have reacted to that. Excuse me. An example of how this works out is there was probably a year's worth of discussion about whether or not we should have implicit or explicit state transitions. And one of the bits of feedback that we got from Vulkan implementers at the time was almost everybody was misusing barriers. And also being a web-facing language, we wanted to make sure that it was easy for people to get things right, because we see that people don't always have access to the hardware that they're targeting, which is kind of faux pas in the graphics world, but we are talking about the web here. So that heavily influenced our decision to have this API be implicit in its state transitions. Another example is we have a new text-based shader language that we call Wigzil. And there was a lot of discussion about this, fairly contentious discussion too. And initially, Google advocated very strongly to use SpearV as our shading language. But as those discussions wore on, we started to realize that, the web is a platform where view source is kind of built in by default. Everything about it is textually based. We saw really good pickup of WebGL and GLSL shaders through this. It enables tools like ShaderToy, and it's really beneficial to beginners. And so we eventually came to the consensus that we did want a text-based shading language. And that turned out to be really useful for applying workarounds during cross-compilation later on. I'll talk about that in a bit. So now getting into our Vulkan implementation, like I said, Dawn is Google's implementation of the API. Chrome uses Vulkan as the backend for Dawn on Chrome OS and Android, and we will eventually ship on Linux as well. There's some dependencies there that have to do with how the compositor works and whatnot that we're working around. And we do have a fairly minimal set of requirements that we expect from a Vulkan implementation before we can run on it. You can see it up there. We spent a lot of time discussing exactly what those requirements would be, making sure that we're not excluding too many devices. We depended an awful lot on things like Sasha Willen's GPUinfo.org stats to help us ensure that we weren't excluding too many devices, because we wanted this to be fairly ubiquitous. Now, you might ask why we're not shipping Vulkan on Windows, because it does technically work there. Our backend does work on Windows, but we do ship the D3D backend, D3D12 backend for Chrome. And supremely unsurprising, tale as old as time, we find that just some of the D3D drivers are better for certain vendors. But beyond that, we also are developing a browser, and browsers tend to look a lot more like an OS than a game or an app or an engine. And that means we need to have a lot of integration points with other pieces of the OS. In Windows case, it's things like direct composition, media foundation, camera API, stuff like that. And those simply have better, more direct hooks into D3D, as you would expect. It's Windows supporting their own ecosystem. So that's part of what drives the decision there. Now, for highlights, and I should mention, by the way, I was not one of the primary developers for the initial implementation of the Vulkan backend, so this is me relaying information on from the rest of the team. But some highlights about our experience with Vulkan is that we found that the Vulkan spec is extremely detailed, and crucially, it actually is specified as in opposition to some of the other APIs. Whereas most of the time when we had a question about how Vulkan worked, we could go look at the spec. And frequently, if we had a question about how the other APIs worked, we would have to rely on personal connections to those teams. So having the extremely detailed Vulkan specification available in this case was very, very helpful to us. Similarly, Vulkan layers work. They do their job. They're very helpful in catching bugs. We recommend everybody uses them. I feel like that's been a theme of this conference. And also, we found that our collaboration with the Vulkan group at Khronos was very, very good and very productive. They were extremely responsive to our questions. If we ever found bugs, we saw that there was a fast turnaround time. And we really appreciated that, even though we are technically working under different standards bodies. There's definitely no animus there. Everybody's just trying to help everybody else out, and it's a wonderfully productive partnership. More highlights on the shading side. The team who was building our shading language found that Vulkan's memory model was really, or memory consistency model, excuse me, was really well developed. It covered the API and shading language and all the interaction points in between. And as a result, they were able to save a lot of work by specifying bits of the Wigzell shading language in terms of just like pointing at the Vulkan memory model and saying like, this is how things should behave across the board. They also found that the SPIR-V specification was very precise about things like what bytes are accessed when and how the floating point values behave. In some cases, that precision means that it's actually specifying how loose things are, but regardless, it was very, very helpful when spinning up our own specification on top of it, and it inspired them to be similarly precise in their own specifications. As far as challenges go, like I hinted at before, WebGPU is an API, not a game, an app, or an engine, and this means that we simply need to ensure that every possible code path is reliable all the time on every device, which is a Herculean task. We don't have the luxury of skipping out on a fancy particle effect on a buggy piece of hardware because that's something that's happening at a layer above ours. And also, we see all the driver bugs, and we have to find reasonable workarounds or, convince ourselves that they're at the very least safe to leave in place. And also, Vulkan is a bring your own utils API. And so Don gets to build all of the same helper classes that everybody else did. This is not surprising in any way, shape, or form, but it is something that contributes to making our Vulkan backend larger and more complicated than the others. And Vulkan is our biggest backend. It's more than twice as big in terms of lines of code from Metal. And that's actually probably a smaller number than it would have been otherwise, because we do have a fairly large common platform agnostic front end that drives a lot of things like our validation. Now, talking about shipping on Android specifically, this is the part that I was principally responsible for. The big, huge highlight here that probably deserves flashing lights is that it mostly worked literally the very first try. There was some complications that we ran into in terms of just getting things spun up on Android. It's a very different build environment, and getting the correct surfaces back and forth and whatnot. But the moment we had first pixels on screen, I think about half of the existing WebGPU content that I tried just worked right out of the box. And I find this to be a testament to the overall portability of Vulkan as an API, and of course, the team that did that initial Vulkan implementation for Chrome OS. The majority of the issues that we did run into were around resource sharing, because Chrome is a multi-process architecture. And so we need to be able to toss things from the renderer process where all the JavaScript is running to the GPU process where all the driver interaction is happening. And that's something that most applications don't really need to deal with. Something that most applications do need to deal with is we found plenty of new driver bugs as we move to this new platform as well. In terms of finding those driver bugs, having a robust CTS, conformance test suite for WebGPU was absolutely invaluable. This is a lesson that we learned from shipping WebGL. It's something that's allowed it to be a stable part of the web platform for the last decade. It also has a very large CTS and something that we run on our integration systems, and it helps keep us ahead of any breakage that happens. We replicated that for WebGPU. It's fairly large. We have over 100,000 conformance test cases. And every time we would spin up a new device, this is one of the first things we run on it, and it gives us back a very nice list of here are your potential implementation or driver issues. An example of those implementation issues, in this case, not a driver issue, is that the WebGPU spec was designed to guarantee that you could create a surface for the canvas in either RGBA or BGRA. And this was just to ensure maximum portability across devices. Now, due to Chrome's multi-process architecture, like I was talking about, any canvas rendering that we needed to do had to go through a hardware buffer, and turns out a hardware buffer only supports one of those. Now, this was not a problem that we went into blind. We knew that this would happen, and the solution was not particularly complicated. We just do a just-in-time copy when we find that you're using a non-optimal format for the system. And you can check and make sure that you're not using that format by calling this preferred canvas format that we have. But it's an example of an area where we had to do a little bit of additional work on Android than we had on other platforms, although this did apply to Mac as well, just in the opposite direction. Excuse me. So there was a couple of bugs that came about, driver bugs, that we found that certain architectural decisions that we had made within Dawn really helped us work around them. An example of which being, we found a frequent crash on one particular vendor when you had a resource that was modified in a compute shader and then sampled or written to in a subsequent render path. It's not quite that simple. There was a lot of minutia behind it. We tried all the validation and barriers and everything, couldn't figure out exactly what this was. It seemed to be a legitimate driver bug. But turns out this only happened if you were doing both of those operations in the same VK command buffer. To fix this, we were able to rely on a quirk of how Dawn is implemented, which is we don't build the VK command buffers directly from the commands that the users are sending down. This is partially to support the multi-process architecture. We actually build out an intermediate representation of all the commands that WebGPU is going to execute in a command buffer, and then send that over the command barrier or the process barrier once, and have it build out the VK command buffer at submit time. This allows us to see the entirety of what's going to be executed before we begin building the VK command buffer. And so we can see when this particular bug criteria is going to come up. And that allows us to actually split it in two. We can build out one command buffer, split it right before the render pass, build out the rest of the command buffer, and then submit those at the same time. This is completely silent. The user doesn't know what's happening, but it does really effectively work around this class of bugs. Similarly, on the shader side, we had several issues that we were able to completely resolve within our shader cross compiler, which we call tint. An example of this is on certain vendors, we found that passing matrices as a function arg was causing a crash and context loss. And the solution to this was pretty simple. We were able to just rewrite the matrix passing as passing by pointer in our cross compilation. This would have been a lot more difficult to work around if we had made the decision to consume SPIR-V directly. It wouldn't have been impossible. We certainly could have done it, but what it would have involved is parsing out the SPIR-V, building out the syntax tree, looking for this particular situation, rewriting the SPIR-V, and then passing it back in. At that point, you're starting to lose some of the benefit of consuming SPIR-V directly if we're having to go through that much manipulation before we can actually pass it off. Now, we do try to work around any of the driver bugs that we find, but in some cases, it is impractical. So an example of this is we found that if you sent the primitive restart value as an index on a list topology, which doesn't use primitive restart values, then on a certain vendor, it would cause a device loss. There's no reasonable way to detect this. We're definitely not going to scan every index buffer before every draw call to make sure that this magic value isn't there. And it was triggering a device loss way before we ever got into the shader. So what do? Well, this is pretty clearly bad app behavior in this case. The device in question couldn't allocate a buffer large enough to actually have 4 billion plus vertices. And so either it meant that the user put in, or the developer put in the wrong index, or they were using the wrong topology mode. And in either case, that's pretty trivial for the developer to fix. And while device loss is annoying, it's not actually dangerous. We vastly prefer losing the device to having undefined behavior because that's something we can't tolerate within the browser. So in this case, we let stuff like this be. And yeah, it affects portability a little bit, but hopefully this doesn't actually come up in real life very often. It's something that just cropped up in our testing. It's better than blocklisting the entire device. And we do have a block list. We prefer not to use it. But in some cases, even the block list is not sufficient. We know of at least one very old GPU where simply asking, can you Vulkan, is just too much for it. Any call to VK enumerate physical device on this device will cause a crash. At which point, I don't know why you advertise Vulkan support at all. But turns out that in order to work around this, we need a block list to block some devices from checking our block list, because the block list is generated from the information that we get from enumerating the physical devices. This is the type of thing that browsers tend to have to deal with that most normal apps don't. If an average game, suffered from this problem, the user would install it, see that it crashed, uninstall it, move on with life. But we really don't want to do that with something as fundamental as browser. And all of that is just, a high-level overview of some of the things that we had to contend with as we're bringing up this new API on the web platform. And we still have a lot of work to do. As I mentioned previously, we do want to extend out the number of Android OS and GPUs that we support. We want to do a lot more investigation of mobile-specific optimizations. The Google team actually hasn't really done any optimizations for mobile. We just took the backend that was working for Chrome OS, and we're happy that it continued to work. I believe that ARM is going to talk about some optimizations that they've done in this context tomorrow. But there's definitely opportunities for us to do more work there. And then we're going to have effectively a lifetime of ongoing maintenance for this, because it is part of the web platform. And there's certain guarantees that you need to be able and willing to make in order to put something into a platform like the web. We've done this with WebGL already. It's been running for a decade. It's going to run for a decade more and probably beyond that. Because if we removed it, it would destroy a good chunk of the content that was built for the web around that. And we want to ensure developers that we're going to have the same guarantees for this. So we're going to keep working. We're going to keep collaborating. And we're thankful for everyone who's enabling us to do that. So that's everything I'm going to cover today. Thank you very much for being here, and I hope you enjoy the rest of Vulkanized.
Do we have any questions for Brandon or about WebGPU? Okay, hand here in the back.
Hey, I was wondering if you could talk more about older device support, specifically on Chromebooks. I think devices need a Vulkan driver to even run WebGPU, and also Android older OS versions. Like, is there a plan to enable those as well?
Yeah, so in terms of Chromebooks, forgive me, but I do not know the criteria off the top of my head for which Chromebooks we're running on right now. I probably should have prepped that. We don't run on every Chromebook, but there's a pretty good percentage of them that we are able to hit. And I forget, there's some architectural limitations to what we do. Similarly on Android, I gave you the criteria up there. It's Android 12 and up in certain GPUs. And really that is just a function of what have we been able to test enough that we feel confident to ship on. It's just a matter of getting more devices in, more testing. We just want to make sure that we're not going to hit anything spectacularly weird. And even then, there's no way that we can test every potential Android device. So we have to take what we feel is a representative sample, run it through a bunch of tests, make sure that we feel like we've hit all of the really safety critical issues, and then put it out. And we do have the Blocklist functionality that I was talking about, where we are able to pretty quickly put out some signals to say, don't allow WebGPU on these devices if we find that we start getting a large volume of crashes from them, for example. So it's a bit of a moving target, and a lot of it is just what have we tested so far.
Okay, thank you.
So I see that you're recording the Vulkan command buffer during the WebGPU submit. And I guess the reason for that is because you don't trust the user, or you don't want to require the user to do the synchronization properly. So you're doing it all for them. And my question is there any kind of white paper presentation, anything like that, which outlines what you're doing and how you're doing it, and if it's applicable to, let's say, a general Vulkan application? So like a Vulkan application could do the same thing?
I do not have a great answer for you on that right now, but I will absolutely take it back to my team. I'm sure that there is some documentation that we have that outlines the general principles behind how we're doing the synchronization. Whether or not it's public friendly, I'm not sure, but I'll ask about it.
Yeah, I think that'd be very beneficial to Vulkan people.
Come to my presentation tomorrow.
There you go.
Hi, I feel comfortable bouncing back on that because you brought it up a few times. Okay, it's back on. Yeah, so you mentioned Wixel and not doing SPURI. Let's not go there. Let's not discuss the merits of Wixel. That's not going to be productive. As someone who is doing compiler work, I do have trouble with the thing where you don't have a binary IR. Well, the binary thing is not that important, but the fact you have a first-class shading language, and I understand why you do that. And it's your platform. It's fine, but not having a shader IR makes cross compilation very painful, because the idea that you can just do source to source AST high level translation, that doesn't work if you have an IR and you do a bunch of transformations beforehand. So if you have something like GLSL, AC, sure, you can source to source that, and it's going to map mostly one-to-one. But if you have something a bit more complicated, let's say might talk tomorrow, VCC, you end up with code that's nothing like the original source. And because you have source to source and you don't have debug info as a side channel, that makes that very painful.
Yeah, I don't know how much I can comment on this, because I'm not part of the team that has been driving the Wixel language and the tint compiler and whatnot. I do know that we have multiple examples of people who have come in and been able to successfully map over to that. How painful that has been for them, I don't know. But the best I can say is it's not a decision that we made lightly. It was a collaboration between multiple companies. A lot of times it's easy to make locally maximize decisions when you're talking about a single company, and when you're trying to do something standard-based that's involving multiple large companies all coming together with their own ideas about how things should be done and political agendas and whatnot. It does create a different set of criteria that you need to meet that's not always purely technical. So I don't have all the answers for you. I'd love to put you in touch with the shader team so you can actually talk to the people who made those decisions a little bit more directly, but that's the best I can give you for now.
All right, we have one question over here.
You mentioned that WebGPU is designed in a way to allow it to be extended later on. Do you know when or if that kind of extension, if people are going to be able to build extensions soon, or if you're going to start building them?
Yeah, so in terms of extensions, we actually call them features in the API, similar to Vulkan. And it's a mechanism that allows the browser vendors to extend it in various ways. So examples of extensions that we have right now, or features that we have right now, are texture compression formats, and whether or not certain texture formats allow for storage manipulation and float 16 operations in shaders and stuff like that. It's not a mechanism that would really allow for somebody external to come in and like patch in their own extensions. We don't really have an avenue for that. It's just to allow us to extend the API without having to do major version revisions to get there.
You're already doing some extensions.
Yes, we are already doing some extensions. Is that it?
All right, do we have any more questions? It appears not. All right, we're going to transition to our next talk.
Thank you very much.